Okay. In fact, in this segment, I was about to discuss about this query which has come now. That if so, this formula which we had, this I think is wrong. This is incomplete, right? So this is the complete formula which we had derived last class, and the query has come now that if this side is say water and this side is air, so some rho 1 C1 is here and some rho 2 C2 is here. Okay, and as we have, I think in some previous class we told that this product is a very special number or special parameter as such. It's called the characteristic impedance of the medium. Okay, so that's why I'm even writing without a comma between them. So it's a product rho 2 C2 as a single parameter. Yeah. So then this equation tells you that if a wave came like this, it got reflected like that and some got transmitted. So now this, its amplitude is B1, its amplitude was A1, sorry, was not required, and this was A2. And this ratio of the amplitude is this portion which we were talking about. And the doubt came from the fact that if we see that a sound wave is coming from say air to water, then there is a positive, so this term will be negative. So in that case rho 2 C2 will be much higher. For example, in this case, water case, rho 2 is around 1000, right, 1000 kg per meter cube, and C is around approximately 1500, right, meters per second. So it's a very huge number as compared to here it's around 1 and here it's around 350. Okay, so if you see that, so this value approximately is 400 or 415 usually it is taken, and this is around 1.5 into 10 raised to 6. So that's the ratio. And then now if you put that thing here, if it is coming from air to water, then this number is positive, right, because rho 2 C2 is bigger. Now what physically that thing tells you is, see, a wave when it hits the a denser medium. Now only the density is not a factor. A medium where it's also dense, more dense, and also it's more incompressible in a way. C deals with that. The more incompressible a fluid is, more the speed of sound in that. Okay, and dense. So both of these things should be told, not only about density but also about compressibility, the amount. So now if that side liquid is more dense and incompressible, in a way it has got an ability to sustain a high pressure at that location, in the sense and then we are talking about these things as pressure waves. So a compression when it goes, so a compressive wave also will be reflected back, so that you know at that point a very high pressure can be sustained. So the other way around, if you see, it's easier to visualize. Suppose you are looking from this side, suppose the wave was coming from this side, water to air, then see this. Now it will be the the air medium on this side will not be able to provide enough what do I call that, I am not getting the word, facility to build up that pressure. That's why you can think in terms of now particle velocity. So if that's more intuitive than the pressure. Now if you think about particle velocity, suppose you are getting into a part where it is almost vacuum, okay, rho c is very very small, that means almost the sound will not propagate there, isn't it? And so the particle velocities there will be almost zero. That's the meaning, right? So at the junction, the particle velocity will be almost zero. And how can that happen? When two waves are coming, one is coming that side and one was going away, but still the summation is like zero. Okay, then that can happen only when they are of opposite phase. So that is intuitive if when you think in terms of velocities, but in pressure also, then you can again go back to thinking in terms of pressure, saying that when it goes from lighter to denser medium sort of, the pressure buildup is possible, but from this side the pressure buildup is not possible. So that is why if you see the two cases, now if I draw, say, this kind of a pressure wave when it is coming, and also a similar kind of pressure wave is getting reflected back, means think in terms of a large difference between rho 2 c, I mean this and this. So almost these are negligible and this is 1, okay. Rho 1 c1 almost is negligible as compared to rho 2 c2, so this is almost equal to 1. In that case, the reflected wave is also like, you know, the same, almost it is overlapping, but just to show that I am showing it, they must be overlapping. Why? Because the summation of them, because the pressure is actually the summation of both, right? So that you will get a high pressure. So this I was talking about. So the water on this side is capable of holding this high pressure. It is able to facilitate that. Okay, so this high pressure, this sustenance of this pressure. Now, when you so this is say air and this is water. And exactly the opposite thing, suppose you see the other case. So now this side is water, this side is air, and sound wave is coming, and again I will draw the similar things. Now this was the pressure, this side is air, so this will not be able to sustain that pressure which this side is trying to build up. So what will happen is this orange one now will be something like this, so that here they will sum up to almost zero. So air is not capable, so a little pressure is built there. So that's how the things are. And so here the pressure will become sort of nullified at this location. Okay, so always it will be zero at this location with respect to time. So this is at a particular instant I am drawing. Okay, it's a snap of the pressure field. Here also at a particular snap, when the pressure amplitudes were like this, at that time only this will happen, and at a particular snap here, if it is here, it will be exactly opposite in that limit. Okay, so that's how the and then these are in terms of pressure. Again you try to see in terms of particle velocity also, so that see here at this location the air particles will not be able to move those water particles much. So almost they will be like zero velocities. They will not be moving much. Okay, but here it's like the water molecule is trying to move the air particle, so it can do that because they are almost like free. So in doing so, they will reverse the thing. Okay. So means here in a way you can say that the particle velocity will be very high in this case. The pressure is very low. Okay. Then okay, so now all these things which we told, no, now we will write the equations and see whether those things are happening, because the way I have drawn here, so that gives you an idea that it's becoming a standing wave this side, and it will happen like that because you see this is also a real number. So there is no phase difference between them. Whatever comes here, this means with the same phase this gets reflected back, and with respect to time also it won't change. So that means you will get a standing wave pattern on this side. So that we will see what the form will be, and yeah. Now just before writing that thing, again to summarize this, so if you are in this kind of a situation where B is positive, a compression wave gets reflected as a compressive wave, here B negative. Okay, so a compressive wave reflected as a rarefied wave. Okay, so that the sum will give us proper values. Okay, now anything else here? That's fine. Now we can go and write the equations for them. So the pressure on the region left side region, the way we have written region 1 and region 2 will be, now I am writing in terms of real values of them. So cosine omega t minus k1x plus b1 cosine omega t plus k1x. That's the pressure field on the region 1, right? At any location x at any time t, right? So now this one, if you expand these things, so that you can see in the notes, I'll post the notes. If you just do the algebra, you will come to a stage where you will get this will be equal to a1 plus b1 square minus a1 minus b1 square cos squared k1x. Yeah, so this is one part. Sorry. Then the other one is a1 minus b1 squared. Whole of this thing under root times cosine of omega t minus phi. I have skipped the algebra here. Just I'll tell you what this thing means. Okay, that means see this one, if you expand, there will be an omega t terms, and here also there will be an omega t terms, but then the kx part of those things, you can think of them as the amplitude to the omega t form, and then you can split them and then you will get to this. Okay, now how to look at this equation. Now you see this this portion is just a function of time, and this function is just a function of x. So that means it is the what requirement for a standing wave, isn't it? Because this is standing, this is just changing its amplitude. This is the shape and this is the size, right? So that's the meaning. Now here if you look at it, it doesn't tell you that information because time and space are clubbed together. Now if you convert this to this form, this nature of the curve is coming out, that the time and space are split. Okay, so that is telling you that what else you can infer from this. See, if B1 is say A1, when the rho 2 C2 was very large as compared to rho 1 C1, right? So that means when we said that this case from air to water type, when, so in that case it will be plus 1, that means B1 is equal to A1 almost. In that case you see here these terms just go away and you are just getting these 2A type amplitudes of pressure waves. So that's what I was showing here like this. Just they get summed up. Okay, and when okay, let's say where do you think the nodes and antinodes will come of this standing wave? And suppose think that okay, let's say at x is equal to 0, what will happen? So this one is 1, so this term just cancel out and this part remains. Even if it is, suppose B1 is not equal to A1, that is the extreme limit, but even in the other cases this is what is the maximum value at x equal to 0, and that is the maximum which you can have. And what is the minimum which you can have is when this whole term goes to 0 and only you are remaining with this, that is A minus B. So maximum pressure anywhere on this side that you get is A plus B. This is the limiting case, so that is why A plus B was 2, but otherwise it will be somewhere between 1 and 2, and the minimum would not be 0, it will be A minus B in the general case. Okay, so that's what you will see here, and then the locations are, you know, so you will have cos squared of k1x is 0 pi or whatever n pi. From there you can get that x is nothing but your n lambda over 2. Is it so? Yeah. So k1x you can write as, you know, 2 pi over lambda x is n pi over n pi. That's what. Okay. So at those locations you are seeing that the pressure is actually getting the maximum value. Those are the antinode points. Okay, and nodes you will get at so these are antinodes, and at x is equal to n means 3 lambda by 4 basically. Sorry, हाँ हाँ बोलो.
Antinode's cos square k1x is 1 and then k1x is equal to 0 by so then cos square k1x is equal to 0.
Sorry, what did I do? So sorry, thank you. So that means how to correct this, I'll just remove this part. So on over that I'll just write it, okay. So cos square k1x is 1. Thanks. Okay. And so here, at lambda, so here these lambdas are corresponding to the one side, okay. So lambda 1 over 4, 3 lambda 1 over 4, like that, okay. In picture, so this is what is one such point, then this is another such point, okay. So lambda by 4, 3 lambda by 4 and so on. Okay, so these are nodes. Okay, that's fine. Anything else which should be okay? That's it. So about the pressure field which exists on the left hand side, or on the side from which the wave is getting incident. Okay. On the next segment we will be talking about what happens to the wave on the other side to which it gets transmitted to. Okay. Okay, we'll stop here.